Well friends, now that we have detailed the longitudinal reinforcement of the column, we'll see the lateral ties here. Okay, so for that, click on this drop down menu over here and click on display design info and click on shear reinforcing and you click on OK. So the shear reinforcement of the column as well as the beam is given, so we'll focus on the column here. Okay, so it's written 0.443 and if you right click on that, you will see the load combination and your stational location. It means that at the bottom or at the top or at the mid. Okay, so longitudinal reinforcement value you can get major shear reinforcement value 0.443 and the minor reinforcement value 0.443 as well. And if you click on summary, so here you can see the different parameters that the SAP has taken for the design of this column. Okay, so you can see the breadth, you can see the depth, and you can also see the elasticity, FC, lateral weight factors, and different things. Okay, and if you go down, you can see the axial force, and biaxial movement. So you can see for this particular column. Okay, and if you go to shear design for VU2 and VU3, you can see the major shear V3. So rebar, the value that we saw 0.443 is actually ASV by S. Okay, ultimate shear force is this much, 64.717 kilonewton. Okay, to use this value to get the spacing of the shear reinforcement. Okay, so it is given as ASB by SB. Okay, so if we open okay, so I'll show you this AutoCAD drawing. So you can see this is a typical column and you can see the bars have been lapped together. So this bar and this bar are lapped and these lines represent the shear reinforcement. Okay, so ASB represents the area of a single stirrup and S represents the spacing of these stirrups. Okay, so we'll use the Excel sheet again and let's delete these things. Okay, so we got ASV by SP at 0.443, right? So 0.443 and this is the value of ASV by S, right? Okay, so we got two unknowns here and only one equation, ASV by SP is equal to 0.443, and we cannot find two unknowns from one equation, right? So in that situation, what you have to do, we have to assume one thing and find the other thing with the help of that assumption. Okay, so let us assume ASV over here and we'll find the S, right? Okay, so ASV, if we take 8 mm diameter bar, okay, so let's take bar, right? So if we take 8 mm bar and it's the, if it's the two-legged stirrup, then the area of that stirrup is ASV is equal to, you can get the value as, so it's a two-legged stirrup, so it's 2 into pi by 4, that is 3.1416 divided by 4 into, so this value squared, right? Again this value and hit enter. So it's basically 2 into pi by 4 into 8 square, right? Okay, so this is the value of ASB for 8 mm diameter bar. So now we get that 100 by S is equal to 0.443. So S is equal to, so this implies, so which implies S we get as, this is equal to, so this value by S is equal to 0.443. Therefore S is equal to this value divided by 0.443, right? And hit enter. Okay, so we got the spacing value as 226.9327 mm, right? So it means that we can vary the spacing of our stirrups up to 226.9327 mm. Okay, so how we detail it, we don't use this spacing because it's very much high. Okay, it won't make our structure safe. Okay, so how we detail it, let's see over here. So this is the column and here you can see that, so this column has been divided into three zones, the lower X zone, the mid Y zone and the upper X zone. So what is X? So you can see that X is greater of H by 6, where H is the height of the floor. Okay, so from the top of the bottom slab up to the bottom of the top slab, right? So X is greater of H by 6 or larger lateral dimension of the column. So larger lateral dimension of the column means if your column is 500 by 300 mm, then you take 500 mm for this B value. Okay, and C we take 450 mm. Okay, you calculate all these three values and take greater of these three values and take that as X, and you got X here as well, and you can find Y. So Y is equal to H minus 2 into X, right? So you can get this value, and this value. Suppose that this X value is like 600 mm. So let's take it as an example. So up to 600 mm from this floor level, we'll put our stirrups in 100 mm center to center. Okay, and in the mid Y portion, what we'll do, we'll place our stirrups in 150 mm center to center. Okay, and in the upper X region, again we'll put our stirrups in 150 mm center to center. Okay, so why we do that? It's because okay, so let me draw this column for you. Just turn on the ortho mode, and if this is your column, and if we see this shear force diagram for this column, it will look similar like this. Okay, so let's turn off this, and okay, so this is your shear force diagram for the column, and you can see that the shear force is higher at the beam column junction and is lower at the mid portion. So that is why we place the stirrups closer near the beam column junction, and we place the stirrups at the farther positions at the mid portion of the column. Okay, so X region 100 mm center to center, that is 4 inches, and Y region 150 mm center to center, that is 6 inches. And again in the X region we do the same thing. Okay, however, if this value comes like 75 mm, let's suppose that this is 75 mm, in that situation we place the stirrup at 75 mm throughout this column. Okay, so we cannot go greater value than that comes from this formula, right? So this is how you detail your stirrups, and in the next video we'll see how you can detail our beams.